Hello and welcome to this lecture. We are going to see some very simple examples of matrix powers which are very intuitive and very easy to understand. Okay. So, here is the example. We will begin with scaling. Okay. So, we remember scaling, right? Scaling is basically a matrix which is alpha 1, alpha 2, diagonal matrix. Okay. This is a diagonal matrix. Off diagonal elements are 0. You have alpha 1 in the first entry, alpha 2 in the second entry in the diagonal. Okay. So, pictorially if you see 1 0 gets multiplied by alpha, maybe alpha 1 is less than 1. So, it gets inside. 0 1 gets multiplied by alpha 2, it goes to 0 alpha 2 and you get you just go scales in this direction. Okay. So, this is scaling. Okay. Now, what happens when I scale again? Okay, when I repeat the transformation again, okay, it is very easy to see, right? When I scale again, this alpha 1 0 is going to get multiplied by alpha 1, so I will get alpha 1 squared 0. Similarly, 0 alpha 2 is going to get multiplied by alpha 2 again, so you will get 0 alpha 2 squared. And that is also true when you multiply this matrix again by itself, right? Alpha 1 0 0 alpha 2. If you multiply it with alpha 1 0 0 alpha 2, you will get alpha 1 squared alpha 2 squared. Okay, I leave that as an exercise to you. Use the matrix multiplication and try, you will get 0. So, diagonal matrices are very easy to take powers of. When you take powers, because it is diagonal, you can ignore the off diagonal elements, they will always be 0. The diagonal elements will keep going to higher and higher powers. Okay, so this is a very useful and simple property. M of t power 3 will become alpha 1 power 3, alpha 2 power 3. You can see it pictorially here. You can also see it by the algebra of matrix multiplication. In general, even if you do it n times, you are going to get alpha 1 power n 0 0 alpha 2 power n. Okay. So, the easiest case for power is diagonal. Okay. The next easy case, it turns out, is rotation. Okay. So, here is rotation by theta naught. You have a point, you have rotated by theta naught. Okay, you got cos theta naught, sin theta naught and minus sin theta naught, cos theta naught. What will happen if you rotate again by theta naught? It is equivalent to rotating the original point by 2 theta naught, right? What is that matrix? It has to be cos 2 theta naught minus sin 2 theta naught, sin 2 theta naught, cos theta naught. Okay, I will leave this as an exercise to you. You use the trigonometry knowledge you picked up from your previous math courses to show that m of t into m of t square will actually be this. You will have to use your formula here. Cos 2 theta is cos square theta minus sin square theta, sin 2 theta is 2 sin theta cos theta. You use that and you will get this. It is easy enough to show. Okay, but even pictorially it is very easy. What happens to m of t power 3? It is the same as rotation by 3 theta. What is m of t power n? The same as rotation by n theta. Okay, so you get m of t power n is cos n theta naught minus sin n theta naught, sin n theta naught, cos n theta naught. How do you prove this in general? You can use something called induction. Okay, so you assume that this is true for n and then you say m of t power n plus 1 is this guy multiplied by this guy. When you multiply this m of t power n by m of t, you can use your trigonometric identity for cos a plus b and sin a plus b and show that you will get cos n plus 1 theta minus sin n plus 1 theta, etc. So, this is also an exercise. Those of you who are interested in such proofs, try those proofs. Okay, but otherwise it is a very intuitive result to see. So, we have seen here that scaling and rotation are very simple examples of, for matrix powers these are very simple. But leave alone rotation, but diagonal seems particularly simple, right? When you take multiple powers, diagonal seems very easy. But how will the general cases look? Do they look like a diagonal? Do they have these kind of properties? Let us see, you will see that they seem to have some properties, but not quite as easy as diagonal. So, let us see a few very interesting examples. The first example I will see is a matrix 1.5, 0.51. I am picking these examples very carefully. Later on, we will see why these examples have been very carefully picked. Okay. So, for now, let us just start with this example and see what happens. Here is a squared. Okay. So, this all I have done numerically. So, that is another part of it. All this you can do numerically in packages. We will see that in a later lecture. Okay. So, a squared is this, a cubed is this. Okay, so you see what is going on here. So, I am just multiplying this numerically to get these answers. A power 4 is this guy. A power 8, if you keep multiplying again and again, you get this. Do you notice what is happening here? The entries are blowing up, but they are all becoming close to each other. So, here is a power 16. So, you notice that all 4 entries are becoming closer and closer to each other, but they are all blowing up. Okay, they are all growing, maybe even exponentially in n. Okay, so this is the observation. A power n for large n in this case seems to be equal in all 4 places and the value grows with n. Okay, in this particular case, it ended up being this way. Okay, so you can see it is very different from what happened in the diagonal case, right? The diagonal case we had a power n, but then the off diagonal elements were always 0. Okay, here it is, all of them are becoming equal. Okay, Here's another example. So, I am picking the same example as before, but I am multiplying it by 0.5. Okay. So, notice what this innocent looking 0.5 does to the property here. A squared is, some value, numerically done it. A cubed is some value like this. They are also seemingly becoming closer. Look at a power 4, it's much closer, all 4 values, they are falling. A power 8 is, becoming closer and closer to 0, right, 0.0505, etc. A power 16 is 0.005005, etc. All of them are becoming really, really close. The differences are going to show up in the later digits, not up to this accuracy, okay. So, notice the difference between the previous and the current case. The previous case, you had an unstable sort of situation, things were blowing up, okay, but all 4 values are becoming equal. Here is another case where you have a stable situation, all happened because of this magic 0.5 that multiplied the original matrix, okay, and suddenly everything became 0. So, here again a power n for large n is equal in all 4 places, but the value decays with n, okay. So, you may be tempted to think this is the only thing that can happen, but it turns out other interesting things can happen. Here is another example, okay, 1, 1, minus 1, 1, okay, the first time a negative number makes an appearance, and here you will see very, very interesting properties. Notice what happens here. A squared is this guy, a cubed is this guy, a power 4 is this guy, okay. So, you notice this diagonal, off diagonal sort of thing happens in some interesting way, and if you go to a power 5, a power 6, a power 7, a power 8, again some sort of a similar pattern shows up. The numbers are blowing up, okay, that is okay, ignore the blowing up for a while, but you see the patterns of zeros are periodically repeating, and this happens over and over again. The pattern of 0 periodically repeats, and there is a periodicity in this power. Some sort of a periodic pattern is showing up in this case, okay. So, 2 by 2 matrices which are not diagonal can show strange properties when you start doing powers, okay. You can have a periodic property like this, some sort of a periodicity, okay. Here is another case, yet another case where you will see very interesting properties. So, 1.501, okay, this matrix, if I keep raising it to powers, notice what happens. The diagonal remains the same, it is always 1, and then there is this lower off diagonal element which is always 0, but that upper off diagonal element keeps increasing, and that is increasing linearly, right, 0.51, 1.52, and this pattern continues, okay. So, a power 9, this, etc. Even a power 12 you see 1, 1, 0, 6. Here is yet another, there is no, in the first 2 cases, the thing was blowing up very quickly or falling down very quickly. In the second case, it was periodic, 1, 1, minus 1, 1. And here is another case where some part of it is staying the same, some part of it is growing linearly, okay. So, it seems like this is the pattern, okay. So, this is a pattern, we haven't proved it yet. Actually, you can prove it by induction, it is not very hard to prove this. So, here is another interesting thing. So, where are all these things coming from? How do you make sense of this? Is it possible if I give you a matrix for you to tell you what will happen to the powers? What will happen to a linear system which evolves according to this matrix, right? What will happen to the state evolution for such a matrix, okay? So, these are very, very interesting things, and you can study these by studying eigenvalues and eigenvectors, okay? And to do that, we need some background. There are 2 pieces of background. The first piece is very easy, it is just something called matrix algebra. We won't spend too much time on it, we will just describe it as being similar to polynomials. The second piece is a little bit more complicated, is the notion of complex vector spaces. That also is very easy, I won't spend too much time on it, I will simply say analogies to the real case, okay. So, let us just quickly see those 2 things and we will close this lecture, okay. First thing is algebra of operators, okay. So, you need to have a little bit of comfort with this. So, if you have a lot of operators T, T1, T2, etc., and I is the identity operator, we have used the identity operator, right, it is just input equals output, okay. So, it turns out operators or matrices, you can add them, subtract them, and you can multiply them. Generally, you can't divide, okay. So, because many matrices are not invertible, so you can't divide, even if it is invertible, there is this problem that AB is not the same as BA, right. So, AB becomes not equal to BA in many cases, we have seen that in matrices. So, it is not the same as numbers, matrices are not the same as numbers, they have all sorts of curious properties, AB can be 0, BA can be non-zero, all sorts of interesting properties, right. We also saw another example where AB became A, right, all these and B was non-zero, B was not 1, all sorts of interesting things can happen. So, but this algebra is a very interesting algebra. You can do a lot of things with just by addition, subtraction, multiplication. Here is an example. First of all, this distributivity is true. Associativity is also true. I have not spent too much time on it. You can multiply in any order and you get the same number. Okay, so that's also something you should remember. The matrix multiplication is associative. If you have a multiplication of matrices, you can multiply them in any order and you will get the same answer. Okay, distributive is very easy to see. Identity commutes with all. So now what is commutativity? So we saw generally matrix multiplication doesn't commute, right? AB is not BA. But if one of them is identity, then IT becomes the same as TI becomes the same as T, right? So whether you multiply identity on the left or on the right makes no difference, you get the same thing. Interestingly, you can also do polynomials in T, because see, polynomials, it's enough if you add, subtract and multiply. So you can do polynomials in T. You can do operations like this, T plus I into T squared minus 2T plus 3I, right? You can multiply like a polynomial. So you multiply these two, you get T cube. Multiply these two, you get minus 2T square, and then you got the plus T square. So that will cancel and you will get minus T square. Just make sure you can multiply, just like polynomials. Just watch out for the non-commutativity, right? If T1, T2 is not the same as T2, T1. So you have to watch out for that, but other than that, you can deal with polynomials as such. Okay, so once in a while, we'll have to use this when we study matrix powers in algebra and all that. Okay, but all such algebraic operation results in other operators. Okay, the next piece of background we need is this notion of a complex vector space. So far, we've always had vector spaces over the reals, right? We've just used real numbers as scalars. But if you remember the introduction, any field can be a scalar field, and complex numbers, you can also do addition, multiplication, subtraction, division, all of them you can do, right? So complex numbers can also be scalars. Okay, so the set C2 is the set of all xy. However, now x can be in C, y can be in C, okay, where C is the complex field. Okay, so this becomes a vector space over the scalar field C. So this is C2. C2 is defined in this fashion, much like R2, xy, where x is in R, y is in R. Now here x becomes C, y becomes C. Okay, all the properties required for vector addition, scalar multiplication can be verified. Okay, I'll leave that as an exercise to you. You can quite easily verify this. Here are examples of a vector. You can have a vector which is 1 plus I, 4 minus 2I, or just 4, 9. Remember, every real vector is also a complex vector, right? Because real numbers are contained in the complex numbers, right? You can also have more fancy looking complex numbers like, e power I pi by 4, e power I pi by 6. We've seen these kind of complex numbers. No, they are on the unit circle, right? So you can have these kind of complex numbers as forming vectors. You can also do operations. You can do linear combination, which is the most critical operation, right? So here is an example: I times 1I plus 2 plus I times minus I minus 1 minus 2I. You will get this, right? I into 1, I into I is minus 1. Right, so this becomes just I minus 1. This 2 plus I into minus I, it's minus 2I minus I square, which is plus 1. So it becomes 1 minus 2I. If you multiply these two, you will get another complex number. Okay, so if you add up all these things, you get 1 minus I minus 1 minus 5. Just simple complex number arithmetic. Everything extends naturally. Okay, R2 is contained in C2, so every real vector also belongs to C2. And all these notions also carry over, right? Linear independence, subspaces, bases, dimension, other such definitions, all of them carry over to C2. Okay, so I'm not going to spend too much time, except whatever we did with R2, you can do with C2 also. It's very easy to see that. Okay, so operators in R2, how do they look? A linear operator T from C2 to C2 will have a range. It will also have a null. And you can do with respect to the canonical basis. Remember, the canonical basis remains the same. 1001 is still the canonical basis, except you can multiply it with complex numbers. Okay, so this T of 10 becomes a complex two-dimensional vector. T of 01 also becomes a complex two-dimensional vector. So the matrix becomes a matrix of complex numbers. Aij is complex. Except for that, the basis is the same. Linear combinations, all of that you can repeat as such. So T is invertible if rank T equals dimension of range T is 2 or null T is 0. An elimination to find the basis for the range, and null also. How do you find null? You can solve Ax equals 0 in the complexes, right? You can do everything just like you did for real. Okay, so that let me just conclude with a couple of examples. Find the range and null of these operators in C2. You can just do this elimination. Maybe I'll just show that and we'll stop. I'll show it for 1 and we'll stop. I'll pick up the example 2, which looks easy enough to do. Okay, so the example we have is I1, 1 plus I, 1 plus I, right? So is that the correct example? So if I have to do the range, how do I find the range? I have to do column 1, which is I1, and column 2, which is 1 plus I, 1 plus I. Okay. So, I can change column 2 to column 2 minus column 1 times 1 plus I divided by I. So, you will get I1 here, and then this will become 0. Okay. Column 1 into 1 plus I divided by I. So, it is 1 plus I minus 1 plus I divided by I. Okay. So, depending on your comfort, you can do it in various ways. You can multiply this here, you will get I minus 1 minus I minus 1 minus 1 minus I by I. Okay. So, this and this cancel, you get minus 2 by I. What do you think that is? You can multiply and divide by I, you will get just 2I. Okay. So, that is 2I, so that you will get here. Okay. So, that is enough. So, the range has a basis which is I comma 1 and 0 comma 2I, which is also 0 comma I. Okay, that is the range basis. How do you do null? For null, you have to solve this equation, right? Ix plus, okay, you do not have to solve anything here because the basis dimension is 2. So, rank is 2, so null will be the origin 0 0, just the 0 0. Okay, let us not think of it as origin because this is no complex, it is not like R2, right? You can't draw it on a plane, right? Every coordinate is a complex number, okay? It is a complicated thing to draw, we can't visualize. So, null is just 0 0 from that. You can also find, null interestingly. So, maybe the other case, yeah, maybe I picked this carefully. So, let's do the null space for I1 and 1 plus I, 1 minus I, okay? I1, 1 plus I, 1 minus I. So, in this case, let me do the null for you, maybe this is interesting. Let me do the null for you, null of this guy. So, I have to solve for Ix plus 1 plus I y equals 0 and x plus 1 minus I y equals 0. Okay. So, what do? You just do multiply this by I and add, okay, right. So, this is equation 1, equation 2, I can do I into 1, right. So, this will become minus 1 and then I can add it to 1. So, I hope that is clear to you, okay. So, if you do this, or maybe I will do it more carefully. So, 1 minus I into 2, right, I can do this. So, this way it will cancel this here and this I will have to do as 1 plus I minus I into 1 minus I, I am doing it laboriously just for your comfort, y equals 0, right. And this actually, if you look at it, it will end up cancelling. So, you will get 1 plus I minus I plus I squared, but what is plus I squared is the same as minus 1 to y equals 0, which is the same as 0 equals 0, okay. So, these two equations are actually exactly the same. So, you can just ditch this equation, worry about only the one of the equations. So, you take the first equation, so you get x plus 1 minus I y equals 0. So, this is the null space. If you want to write it in terms of the basis, you can pick y to be an arbitrary y, right. So, let me write down the solution. So, y is taken as the free variable and x becomes minus 1 minus I y, okay. So, you take y to be equal to 1, you get y to be equal to some k, or okay, leave it like that. So, you get that the null space vector is minus 1 minus I y comma y for any y in complex, right. So, that is how you get this. So, the basis of the null space is minus 1 minus I comma 1, okay. So, you see here we got a basis and we solved it the exact same way. So, you can do that here also, okay. So, that is the end of this lecture. Hopefully, this background of operator algebra, simple multiplication of matrices and complex vector space was reasonably clear to you. Armed with this, we are ready to attack the problem of eigenvalues and eigenvectors. Thank you very much.